Alright, we're recording. So, tell them that's it. It won't just split.
No, I don't answer them.
You sure? Let me tell you, C1 and C2.
I see it. I know, H, I want to go. Then say, at the end of the day, then the correspondent.
Because look at them happen anymore. Okay. So you tell them machine, you go over and make it clear for
yeah, remember the FM when they check
and the classroom. There's one thing the RAS. They look at small RAS.
Oh man. I said,
eh? Alright. In our class,
or baby. Yeah.
Yeah, it's a imperfect.
Yeah, some say, well, at times, many about the camera, but you need to it, and then you do more questions, because you're not still into the tree where you make it prepare for that.
So you might get good out of 100 if Alright, so as I was saying, we're doing optimization. Optimization, as handled in this module, really is the determining of the maximum or minimum top of a peak or the bottom of a valley of a function. And it is also iteration. So, looking at all the different procedures that we've been going through, everything is really solving systems or solving equations or solving systems of equations. You handled linear systems at first and systems of linear equations. Then you handled solving nonlinear systems, and to solve nonlinear systems you need to do an iterative procedure. You have two general ways. Huh? Oh no, not yet. So do it. You shouldn't be getting it as yet. Check if he's getting. Oh, that means you shouldn't be. Alright, small seat. Ask him to confirm, or I guess I can. No, he can type it here when he sees it. Devon, you're still not hearing anything? Are you hearing anything? Okay, so you're seeing, all right, and you're hearing too, right?
I'm seeing.
And you're hearing? Okay.
Yes, I'm hearing.
So, as I was saying, optimization or iteration, you have you have one main form of iteration, which is called root finding. All right? And root finding has several different ways. The simplest is bisection, and it keeps going to more complex options. And then you have the option of fixed point solutions or fixed point iteration. Fixed point iteration is actually a technique sometimes that you would have some people learn in undergrad, where you have to solve for something, you plug it in and you get back an answer. Sometimes it's taught, but it may have just been taught at a glance. But most of the iterative procedures fall under root finding. Now there's another way in which we solve functions. Instead of solving for an unknown, you can solve for when the unknown is at a maximum or a minimum, and that's called optimization. Optimization in nonlinear systems always has to do with a peak or a valley. Optimization for linear systems never have to do with peaks or valleys. A linear system can be pictured like either a line or a plane, right? Everybody understand? It's something that is flat. So the best really just means which corner. If it's a plane, which corner is best. So there's a corner that's going to be the highest. There's a corner that will be the lowest, because it's just a rectangle. It's just a plane in space. Could be a triangle, could be a rectangle, or many-sided. Can be more than 4, 5, 6. Doesn't matter. Just a polygon in space. And all the question is really which corner has the highest value. So that's linear optimization, which I'm not handling in this class. And it's not usually something that is handled in general engineering. It's usually more financial and management skill. It would have been done in a class called operations, research, and management. So those who did that class would have touched on optimizing linear systems. All right. But I just want you to understand the difference. So here, when we say optimization, we are again talking about iteration, and we are talking about nonlinear systems. And it always means a peak or a valley. Peak or a valley can be a 1D, that means on a line, or it can be a 2D, or it can be any amount of D, for that matter. We wouldn't go beyond 2D though. If it's 2D, it's like a contour, like a map with contours, and you're looking for where you have peaks and valleys on that map. Alright? So we've handled unidimensional methods, and the first method was called golden section. The analogy is for root finding would be bisection. Okay? And in those methods, those are bounded solution methods. And for bisection, just as for golden section, you are always reducing your bound by a fixed fraction. For bisection, you reduce it by a half, 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 half. For golden section, you reduce it by 38.2% each time. Not really, it's 68 that you cut, but the reduction becomes 38.2. Let me just draw that so you're convinced of what I just said. I see some blanks. So here is our sorry, that's not over. Should I carry my ruler? Let me work it out now. Let me work it out. You have one? Better. We have some lines from the things so we can follow the lines. Alright. So what golden section does is, thank you, is say you have a curve and you have some ranges. Let's say you want your bound is going to be that's going to be your bound. The first step is always to find the 261.8. It's called the golden number. So this region here is 61.8% of the whole thing. Right? That is 100%. And you also find the other 61.8. So this region here is also 61.8%. And when you do the bound, this would have been called hold on. Try to remember the nomenclature. It's XL and XR. Yeah. So this is XL. This one is XR. And this we call X plus and X minus. You must know if you're looking for a maximum or minimum, and you must know there's only one peak in that range. Just like in bisection, you must know that there is one root in the range. So you know these two values, well, it doesn't really matter what these two values are. What you do know is that you calculate these two, whichever one is the larger is going to fall within the new range. So since this one is larger, your new range is going to be, you keep the old lower, and you're going to move XR to here. So now this is the new range. And that new range has been reduced by 38.2%. That's what I'm saying. Alright? Bisection would have reduced the range by 50% each time. But the point is, both of them, the iterative step is always constant. So Newton and the other methods, you can actually get to the answer very quickly, rush to the answer. But for this case, you always get to the answer at a fixed amount of iterations, regardless of where the answer is. Always takes the same amount of iterations. Alright? Another way to look at it is, suppose, remember, you use an error criteria to say when you're done. So let's say you said I'll be done when X minus and X plus are 0.1%. Let's give you an example. A certain range. You started at 100, you're going to be cutting down. You cut down to 68%, and you cut down to 61.8%, and you take 61.8 of 61.8, and you take 61.8 of that until you reach 0.1%. It's a fixed a number of times. Regardless of your problem, as long as you start with the same range and you have a given error criteria, regardless of the actual function, is going to take the exact amount of iterations. Same thing for bisection, same thing for golden section. Alright? Cutting it by a half, cutting it by a half, cutting it by a half, continually until you get to the answer. Now the other methods is the let's go back to so the parabolic method is like the secant method. Okay? Now remember the secant method, what did the secant make? Not secant, the regular Falsey. Regular Falsey said we are going to draw a line between the 2 points, and where that line intersects is going to be the new bound. That's what regular Falsey did, instead of saying the middle. Alright? What parabolic does is, let me show you. Alright, so so what we do is you find another point, your third point. You can use either this expression or that expression, it doesn't matter which one you use, to find your bound, to find that one of the middle points. And now you have 3 points, and you're going to fit those 3 points to a quadratic. Okay? And you always just replace the oldest of the 3. It's similar to the false position for root finding. Alright? I'm not going to go into detail in parabolic though. And the last one is Brent's, which is kind of a mix. The reason why you kind of have to do a mix sometimes is that whenever you use the parabolic option and you fit to a quadratic, sometimes the quadratic carries you to a value outside of the original bound. And so because it throws you outside of the original bound, at that time you revert back to the golden section and say, stick within your bound. Alright? So you keep reducing your range using the parabolic, but sometimes the parabolic estimates outside of the bounded range, and so you force it back to the most recent sure range that you had. So that's called Brent's method. And you have a Newton method. I'm not going to go into it. Alright, now multidimensional, as I said, is like having a contour plot or a contour map and wanted to find out where the peaks are or where the valleys are. Now, there are 3 ways to solve multidimensional problems. The first one actually, it is actually used, but it's not a method. There is no clear method of being random. So there's a random method, which is you grid out your whole system, you solve for all of them, you have to see which one are the largest. That's very tedious, right? But the thing is, because a contour can seem like a very tedious thing, to have a clear method to get to the solution, sometimes people say they don't even want to think about an algorithm to find to solve a multidimensional problem. But let's do a 2D problem, 3D problem, or 2D, depends how you look at it. 2 independent, 1 dependent. Let's go back. Now, in in 1D problems, I mean one independent, to determine if you have a minimum or a maximum, you just take the second derivative, and if the second derivative is a positive value, it's a minimum, good. And if it's a negative value, it's a maximum. Just like everybody know that y equal x squared y equal x squared looks like y equal x squared looks like this, right? Oops. Sorry. That right? What is that? A value or a hill? Please remember this, because in your mind you just think hill is positive and value is negative. You just have this vibe to say that, not true? It feels natural to think of hills as positive, but remember this is y equals x squared. First derivative is 2x. The second derivative is 2, positive, right? Alright, and if the second derivative is negative, then it's a maximum. Very odd way to speak, that if something is negative, it's a maximum, and when it's positive, it's a minimum, but that is what it is. Okay, smiley face. Let's go back to the slide where we were. Now for 2D, I mean 2 independent variables, you have to use a function called the Hessian. You know, like how you have determinant of a matrix, Hessian is actually the determinant of a matrix, and this is the matrix. The matrix is the second order. It's a matrix of the second order derivatives of the function in that form. Alright? When you take the determinant of that matrix, if it's positive, it's a minimum, right? And if it's negative, it's a no. If both are positive, it's a minimum. No. If the determinant of the Hessian is positive, it can be a maximum also if the second derivative of the x is negative. Alright, everybody see that? Let us use this as a test. And finally, if the determinant of Hessian is negative, then it's a saddle. Everybody remember what a saddle is, right? Okay. And please note, this could have been written the other way, it still holds. What is the other way? Yeah, this could have stated that this could have been y partial y squared, and this could have been partial y squared. Doesn't matter, because x and y are just non-dimensional, the independent variables. So there's nothing about x versus y that you should understand what I'm saying. So it could go either way.
What did you say saddle was?
The saddle is when the Hessian is a negative. The determinant. That means this times this minus this times this equals a value less than 0. Okay? All right. So now, so here's something that when you're doing an optimization problem, you will come to a place where the slope, what you're really trying to do is find where the slope goes to 0. Okay? Now, when the slope goes to 0, at the end of your problem, it's always appropriate to calculate the determinant of the Hessian. Because you want to confirm that it's actually a maximum or a minimum. Understood? Whenever you do your algorithm, a final step in your algorithm should always be to calculate the determinant of the Hessian, and from that determine if it's a maximum, a minimum, or a saddle. Because the procedure is not going to, all these procedures, the unique part of them is not going to actually tell you necessarily if it's a maximum or a minimum. It just tells you that you're at a 0 slope. So you need to know, do one last check at the end to say it is a maximum or minimum. You may have remembered when you're doing root finding, you're told to check at the end to make sure that you're not at slope close to 0, because you know that's 2 roots actually. Remember that? So there's these little things that you have to be careful about. Okay. So to understand multidimensional optimization, the best way to look at it is to look at the contour like what you have here. All right. So what is univariate optimization? It is it's one-dimensional optimization repeated over and over again. So what you do is you look at this plot here. Everybody, let me point first. Everybody see what I'm pointing to? The number 2, line 1 to 2. So I'm going to call that Y12. Y12 is a value for Y right here. They call it Y12. Everybody see that? And then I'm going to call this Y34. I'm going to call this X1. And this would be X23. And this is going to be X45, X6, and so on, right? Everybody seeing that? Now, what we do is we're going to do optimization on one-dimensionally first. All we do is we're going to make Y a constant. We will, so let's say you had a function f, the function of x and y. I'm going to say z is a function of x and y. I want to know when z is, or the function is maximized, right? So what we do is the dimension going to the board is coming out at the z. Alright? And the contours represent lines of constant z. Clear? The blue lines, these blue lines here, lines of constant z. Alright? So what we want to do is, this is our 2D problem, or 3D problem, pardon me. We're going to convert it, sorry. So we're going to convert this to a 2D problem. Z is equal to a function of x. Y12. Y12 is now a fixed value. So it's really z as a function of x alone. X is now a variable, y is no longer a variable. Am I clear? So that will be a line. And that line would be on this line here. Everybody see it? It would be on that line. So that line, as I move on the line, really what you're seeing here is here you may have a low value. Let's say this is a maximum. There's a low value of Z, and Z keeps increasing, and at this point Z is at a maximum on this line, and then Z starts decreasing as you continue moving on the line. What am I changing that causes Z to go up and then down? X. Good. So it's a 1D problem, right? So Z is equal to the function of X, yes? Yes, so it's no, you wouldn't really apply. You wouldn't be applying a partial derivative. All we're saying is you have the function, wherever you have y, let's say you decided you're going to start at y equal 1, everywhere you have y, you just plug in the value 1. So now it's just z is equal to a function of x. And that function now is a line rather than a plane. And on that line, you are going to find the maximum, and you just use the golden section to find where the maximum is. Alright? Having found the maximum on that line, then that is now your new starting point. Whatever the x is, you're going to make that x now a constant. And you're going to change your, so the first one was the first iteration, so it's like iterations of iteration. So the first set of iterations was for varying x's. When you found x max, so I'm going to call it x max 1, then you're going to say z, I'm going to call it zx1, and then I'm going to say zy1 is going to be f x max 1. That means the max I got when I did this one. And now y is a variable. And that now, in this case, is going to be this line. Right? And on this line, let's say I started here. The z is going to be low, and the z increases and increases, and then it reaches here. The z stops increasing and it starts going down again. So on that new line, I found where the maximum is on that line. Wherever the maximum is on that line, that becomes my new constant for y. And on that, I find the maximum for x. And wherever the maximum for x is, becomes the new constant for x. And on that line, I find the new constant for y, and the new maximum for y. And I keep doing that, and it eventually carries me to the peak, or the value of the function. Understand? So it is a combination, as the statement says here. Please, anybody not understanding what I'm saying? Eh?
Sir, maybe if your diagram was a bit bigger.
Alright. Let me do that now. I'm going to take the diagram. I'm going to move the diagram and put it on a Just to find the maximum Z.
So at the end of it, you should get the maximum Z, not before. So suppose the T wasn't really there, but it was like further to you, like down here. And then they continue past it.
No, you're not going past it. Alright. As long as you find the maximum on where you are. Alright. There's a caution. I appreciate what you're saying. First of all, just like for golden section, you have to have an understanding that you have one peak. So you have to carefully determine the bound of your problem, where you have an assurance that you have one peak or one value in it. Where it is you don't know, but you have. Where exactly it is you don't know, but you know generally where it should be. And that's how you normally start it out. Okay? So it won't carry you somewhere else. Let me go back to the picture again, just to repeat the whole procedure. So Richard asked me to blow it up. So first, we use some different color. I won't like the red.
So, sir,
Use red. Yeah, orange.
what the actually kind of point
Two.
yeah, the point two
Yeah.
is the coordinate, is the ZX coordinate.
And two. All right, that's not the best color. Let me go back to red. Oops, sorry. Yeah, repeat your question, Shannon.
Yeah, so I'm saying I'm point two. Our actually find is it that we already know Z at that point and want to find X at that point?
We don't know point two.
Anything about it?
No, all we decide is we're going to start at this Y.
That one, and that's unknown.
Right. It's like it's a constant. It's just like when you're picking a rate, like you're picking it's like when you're picking a bound, right? So you're going to start somewhere. So we start with this Y. And on that Y, we find the maximum Z. But it's not really, you don't really care what the Z is. You just care that there's a maximum there. And then, what you care about is what the X is at that location. And then once you've found the X, that becomes now the new known that you're starting with. And now you don't care about this Y anymore. You don't use this Y. Finish with this. Okay? Finish with that. Now you care about the X. So for the X now, this is now the line that you're going to be trying to find where is the peak on that line. So it's really, when you did the first one, if I was to do what's called a section in map reading, we call it a section. So I could do a section here, let me call it a section AB. Map reading, just some, do the geography or cartography or military terms. So what I'm going to do is I'm going to draw . I'm going to draw z as a function of x for y equal y12. Okay? Now what you would have is something looking like this. That's what this line here is representing. So at a certain value of x for that y12, we ended up with a peak. Alright? That peak, whatever the x is what is important to you. That x now will be used as some initial parameter for this new line here. Use my arrow for this new line here, and you find the peak on that line. And as long as you keep doing that, you will get to the peak, provided there's one peak in the system, or you get to a peak if there's more than one peak in the system. Now, this class isn't to tell you which peak is a valid one. Your discipline is supposed to tell you how you distinguish your various answers. Because math is just a tool. It's not, it don't tell you everything. Alright?
If we forgot those functions, right?
Yeah.
We could also, for example, we know that at the peak, the gradient will be zero, right? At the peak or the chop. So we could actually find the first derivative of our z equated to zero and find the x value required constant.
Yes, ma'am.
We'll get the same answer.
Right, but remember what iteration means? Iteration is for cases where you cannot analytically determine a solution. So you know that the peak of a function is where the first derivative is equal to 0. Just like how you know you can find the root of a function by setting the expression to be equal to 0. But not every function you can solve explicitly for the variable, and similarly for not every function you can explicitly determine the derivative and solve for when the derivative is equal to 0. Okay? Because what you'll end up with is derivatives at different locations in your function, and you can't find a way to get them grouped together. So that's what the iterative procedure is about. Alright? But that's correct still. Alright. But it may be, Shanara, as you're saying, it may be that the function z, it may be that you cannot do the second derivative of the function z, but you can do the second derivative of when one variable is set to a constant. And in such a case, you could do this procedure. Alright? Artwell and Jordan and so forth, you know, following along?
Sir, but I think I finished explaining what's on the diagram.
You want me to finish explain? Okay. So you find the peak for this new function that would have been z as a function of y for this x max 1 or x max 1, 2. Okay? And then you would have found the y max. And this y max is now going to be used for the next function. The next function would be z as a function of x again. Right. So it would be z, let me call this z3. So this would have been z1 This would have been Z2 functions. This is now Z3. Z3 is a function of, what would it be a function of? Y.
Y.
For a fixed x, okay? For, no, this is going to be a function of x, pardon me. For a fixed y. For y3. Let me just say y3. Okay? Because you would have determined y3. It's a third step, right? And then this would be this line would be y4. Oops. Y4. And y4, let me write it. Y4, Z4, pardon me. Z4 is going to be a function of y, because you realize it is, for this function here, it is y that is changing as you go along the line. And it's for x4, right? That means the fourth set of iterations for x4. Alright? Okay, Judan? And you keep going until you get to the location. Yeah.
In reality, will be older, basically have the contour and the value of the reach one.
Huh?
In reality, the older you have the contour that the guidance, right?
No, you wouldn't have the contour.
Would we be going until the one after the master, we see that the function starts to increase?
Yeah. You go until when you get to the x, and you try to find the y for that x. How should I say? Okay, look at it this way. You started at this value. This is the value you're given. 0.1. And with 0.1, you found this to be the peak. So now, this is what you're given for your y. This is where you're starting. Remember, you're starting with y1. It's a given value. Same y1 is here. But now you're using this x. Y1 is fixed, okay? And you find y3. Am I clear? This location is y3. The peak of z as a function of y. So let's say this was here, this value was y12, and then you found this to be y3. Understand? Understand what I just did here?
So you find the first intersection, because why couldn't it be the outer?
The outer what?
Outer, further, the following y1, point at y1.
This is y1, right here. Or this is y1 really, but it's the same y. That's why you want to call this y2, that's fine.
Alright. That's that point.
Yeah.
The following goes all the way up. Why not the outer ring, blue ring?
This one?
Yes.
No man. The peak, if you are on this line, it's hard for you. Map reading would help. But it's a rule of thumb. You understand what a contour is, right?
Okay.
A contour is a line of constant height, or in this case, line of constant z. So the rule is, whenever a line becomes tangential to a contour, you're at the peak or the minimum of the line. So this line here, it becomes tangential to a contour. It's cutting through contours, but when it gets here, it becomes tangential. So we know that it's at the peak for the red line. Okay? Let me keep going. So what I'm saying is, eventually, so here, this is where you were at y12, and you solve for a y3. And then using the y3 for this x, starting with now x2, you're going to find x4. Eventually, you'll find that the value you start with is equal to the value of the peak on that plot. So eventually you'll end up a place where like if this, let's use back the top plot. Let me go, where am I? Where am I? Oh, here we go. Using back this top plot, you'll end up a place where you may find that this is the previous y, and the peak you find to be almost at the same location. And then you say, okay, I'm now at the peak. Understand? Now here's some little...
Your consecutive deltas will become
right. Now, this is for PhD stuff if you want to do maths PhD. Sometimes I do this stuff.
Yes, please.
No? Okay, good. So here's a little... Wait till Brandy's come back.
pass on it,
Hmm?
pass on that one.
Yeah, you pass on this one. So, alright, so somebody might be interested in it. There are some little hints here of ways to improve your optimization. What I'm going to tell you is not even necessarily textbook stated, but you can just see it if you learn to read into things. So here they showed some lines. I don't even know if the author saw what he was doing. But after you do 4 iterative steps, you can project 2 lines and use those 2 lines to estimate where the center might be. It's just 2 straight lines. It may not be the peak, you know, but it's a quick way to get to where the peak may be. And then you do univariate again from that location. Right? And then do it 4 times. And again, where the 2 lines push you to, you estimate that to be where the new peak is. And so forth. But you can have plots that are very contours that are, you know, not necessarily. Let me give you an example of contours may look like weaknesses? Yes, time consuming, that's one. I wouldn't call it. We're going to get back to Newton, you know, so Newton and everything. So Newton was in the previous one, there's a Newton here also. But you can have, let me look at that contour. Imagine a contour. Oops. Doesn't supposed to go so far. I'm not sure I'll give you that assignment. Alright. You may have a contour looking like this. And the peak is right here. Something like that. So you start here. The univariate method pretty much is going to do this. It's going to kind of go around, just like you're climbing trying to stay in the path, okay? So I'm not saying projecting the two lines always gets you to the answer, because if you do the univariate method, it would guess the peak to be somewhere over here at first, and then you say, oh, not quite, and it may guess it to be somewhere here, and then it gets to the answer. This is to segue into the next method. The next method is really the more popular one. Everybody is clear on univariate. So let's read the procedure now. I've explained it, just read it. You start at a certain location. You use one of the unidimensional methods like golden section. Find the max. You define a given x2. And use now, and you find the max for y. And then you repeat continually. Alright? All the other criteria are the same in terms of errors and all those things that you learned for root finding. Alright. Steepest descent. Steepest descent. This is a little different. Steepest descent says, okay, first of all, everybody is going to be introduced to, you may have learned it in fluids. No. Dr. Brown teach someone of fluids? No. Nobody here. You taught your fluids? Oh, he taught chemical fluids too?
Yeah.
So is that 1 year?
Yeah.
Mathematics.
Oh, well, you're not lucky. It was rough though, I know. But when you get the real fluid, that's all I can tell you. It was a bit heavy though, I'm sure. But you should have learned about the function called grad with Dr. Brown. Did you remember that? Okay. It's this symbol here. This. Yeah, grad. Alright, so grad just means gradient. Yeah, del. It's a del. Okay, this is called del. But it's used in different ways. So you have grad, curl, and div. There are 3 different ways it's used. This is a vector. Okay, it really means partial xi in the I direction plus partial yj. And if it's a 3D, you would add k also. That's what grad means. Now, if I say grad z, I just mean this. Okay? But you have something called curl z, which means I, j, k, partial x, partial y, and partial z, and then you would have z, x, z. This is statics-ish. Huh? There's a cross product. It's called the curl. So this one was the grad of z. Now this is the curl of z. And it's just this times this I minus this times that minus that times this I, and so on. And then you have one called the div, which means the divergence. Div is this dot z. Alright? Alright, cool. And div is a scalar. The answer is a scalar. Curl, the answer is a vector. And grad, the answer is a vector. Alright? Grad is normally is operated on scalars, but grad can be operated on vectors also, but you only operate it on each component of the vector. So if I say, let's say I'm taking the grad of velocity, then you'd actually take the grad of velocity in the x, grad of velocity in the y, and grad of velocity in the z separately, not related to each other. But if I'm taking the curl of the velocity, then you would have to apply the expression up here, where this is the velocity in the x, the velocity in the y, and the velocity in the z will be used. Alright? And if you're doing the divergence of the velocity, again, you would need it to be a vector. So to do divergence and curl, the argument has to be a vector. But if you're doing the grad, it can be a scalar, but it can also be a vector. Alright? Don't worry about all of that for those who didn't do fluids. I hope that wasn't too heavy. I know it was heavy, but I hope it wasn't too heavy. Alright, so this is called the nabla sign, N-A-B-L-A, sometimes called the del function. So the nabla is the sign, but the del means partial xi plus partial y, j, and so on, if it's so on. That's what del function means, or otherwise written this way, comma, or otherwise written like a vector like that. Okay? It's called the del function, but the symbol is called nabla. Just like how this symbol is called delta. Alright? Okay. I'm erasing this. Alright, so the univariate method, the steepest ascent or descent does this. It says, calculate the grad of the function. In our optimization problems, we always assume the function to be a scalar. Even if you're going to calculate where the velocity of something is maximum, you either are saying I want to know where the speed is maximum, which is a scalar, or I want to know where one of the components is maximum. One of the components is still a scalar. In all cases, when you're doing optimization, you're finding the optimal of a scalar all the time. Even if it's associated with a vector, you're either finding the magnitude of the vector optimized, or you're finding a component of the vector optimized. But never, you can't define the maximum of a vector as a vector, okay? There's no maximum for a vector where the answer is still a vector. That's what I'm trying to say. You can't have the maximum for a vector where the answer is still a vector. Like there's no maximum velocity as a vector. There's maximum speed. Okay? So, just be clear on that. Because the challenge is, how do you account for, is there something called a maximum direction? There is no such thing as a maximum direction. Right? Okay. So let's optimize. Steepest descent says all you do, you start at a point, you calculate what's called the grad of the point. The grad of the point tells you the direction in which the function is changing the fastest. Best if I pull up an example. Let's do an example. Oh boy. Just give me a minute. Try to pull up an example for you, okay? Jordan and Cleos and Devon kinda with me. A little rough. Hello? Anybody home?
It's a bit rough, but I'm trying to follow.
Okay. Coming. All right. I'm going to do a simple function. Need another whiteboard. Make up another whiteboard quickly. All right, so here we have, I'm going to look at the function, simple function, Z is a function of x and y. I'm going to call that function xy squared. We know the answer. I want to find where the minimum is or maximum. But let's say we just want to find out the direction of steepest ascent or descent. Alright? We're going to start. Let x1, y1. Why does it do that? And x1, y1 equal 2, 2. Alright? What we do, remember we're doing the grad of f, or grad of z. df dx I plus df partial f partial y j at 2, 2. Okay? So take partial f. What's partial f, partial x? Going to be y squared at 2, 2 I plus 2xy. Everybody following? Hello? And that's when you plug in the values, this becomes 4I plus 8j. So the grad of the function at 2, 2 equal 4I plus 8j. Otherwise written sometimes we just say 4, 8. Vector 4, 8. And then put it in curly brackets. This more indicates a position. This is the vector. So you want to conceptualize what that means. Let's conceptualize what it means. First of all, what is the value of the function at that location? What is f at that location? Eight. And we just found at location 2, 2. And we said z or the function is equal to 8, right? Alright, question. Let's say x was equal to 1. What would y have to be for the function to be 8? Square root of 8, which is about little less than 3. Right. This is 1, this would be 3, so it would be about, so 1 would be about here. Following? Let's say it was about a half. If x was a half, what would y have to be for z to be 8? 4? Alright. So 2, 4 is about there. So at a half, will be about there. Okay. For x equal 3, what would y have to be? What's that? Give me an actual value. Less than 1. root 8 over 3 is less than 1. What about for 4? To be root 2 square root of 2.707. Shame on you. 1.4 something, right? About here, and as you keep going, to keep going in that direction, and this would also keep going up like that. So our line of constant z, that means this is the line where the function equals 8. Sorry about it, it's kind of hard. Pardon the bad drawing. Everybody should get the idea. This is about what the line would be, right? The question is, at this location, what's the direction of ascent? The direction of ascent, if this is the contour, ascent is always 90 degrees to it, or descent. Everybody understand that? We actually, so it's either going to be in this direction or that direction. And what this says, let's try to see. Let me use MATLAB. You want me to use MATLAB? Get the actual picture? Octave, I mean. We're stopping it with this one. Come on. We're going to learn about the function called contour. Okay, so let's do a grid. Oh, sorry, you're not seeing what let's put it on. What's going on here? Can I get this? How come? There we go. Everybody have seen that? Since I don't remember, let us do a quick check. So we're going to make a contour plot. Here's an example. So this example okay, can do that. Alright, note. So we're going to say x equal, and I'm going to go from 0 to 4. So I say 0, and I'm going to do indexes of 0.1 all the way to 4, because I want my contour to be tight. And I'm going to make y the same thing. But I always y is the same thing. Oops, didn't want to show it. Let's clean that up. Make clear and start over again. Start over again. X is that. Y the same thing. And now, and I'm going to say Z is equal to X squared, but because I want it to do it this way, do it like that. Hold on, let me check something. I'll make it a little bit cruder. Let me look at X, that's X. Let's look at Y, that's Y. X squared times y. I want to make a vector. Let's do it quickly. I'm doing a vector. I want to do a vector operation. I want to do it properly. So let me just make sure I'm doing it properly. So if I'm doing a vector operation and I want to multiply, so I have my x's, so what I'm going to do is x should be in this direction, and I'm going to multiply by y in that direction. It's like a dot product. And then my answer would be a grid. So I'm multiplying two vectors. I want to make sure I multiply it in the right way. So I have to do a column times the row. If I did a row times a column, I get a single answer. And everybody see what I just said? So if I did this times that, I get a single answer. Because like a dot product, when you do matrix multiplication, it's really dot products. So what I do is the first element times the first element plus the second times the second plus the third times the third, and so on. When I do it like this, it's just going to do this times that and to place it here. It will do this times that and place it there, and so forth. So the first row is going to be just for that x, and the next row will be for the next x, and so on. So I'm going to make sure that my x's are as a column and my y's are as a row. So go back to this guy. It's the other way I had it here. So I transpose. I say x equal y, or x transpose, that's fine. And y equal y transpose. Good. There we go. Now what I want to do is I want to write now z. Z I said was equal to x squared y. Was that it?
Yes, sir.
Alright.
No, x, y squared.
Xy squared. So it's going to be x now times, it's a normal matrix multiplication, but when I'm doing the y squared I have to do this. I have to put the dot. That means square the elements of y. Okay? You can't square a row, you can only square a square matrix. Alright? And what is going to come up is, there it is. So that is now the z for all the x's and y's. Alright? And then I'm going to do a contour. And I'll say z, x, y. Don't see it. It's here, no, but not on your screen, but I'm checking. Give it a minute. Unless I left off something. Oops, crash. So let me crash out of this and redo it. Let me try it again. Now, what I just did still would be let's do it again. Let me see if it's there. May not be. December 4. No, that's from last week. So I didn't get to save it. Let's do it quickly again. X equal, now I'm going to put it in brackets and do the transpose same time. I'll make it tighter now. 4. And I'll put the transpose sign. Alright. And then y equal x transpose. Let me just do help con and z equal x times y squared. That means element by element operation. And I'll just do help contour just to make sure I didn't do the wrong thing. Why it crashed. Oh, I should have put the Z last. So I just say oh man, I don't have to put the range, you know. Contour X, Y, Z. Hello. Waiting for it to come up. Not coming. Graphics toolbox? No, I think so. Oh, there it is. Okay, we just took a little time. Because I start to do some interpolation, which is going to be the next topic, by the way. Got to do some interpolation too. So this is our plot. Let me more do it to scale. Hold on. Make it look square. Okay, there we go. That's square, right? About square. The reason I need to be square is so that you can do the proper gradient. I may even copy it over to that looks square. Alright, let me copy the image. Go back to PowerPoint. All right. Huh? The file? I can. Okay, there we go. So, 2.2 is going to be, I'm trying to see where my, okay, here we go. So 2.2, come on, do that. So go here. So this is 2. Okay, so that's 2. And 2 is right there. Okay, so here Z is equal to 8. If you look carefully, the line, the contour is about Everybody agree the contour is about there? The contour passing through that line will be about there. The slope, the steepest change would therefore be about this. See that? If you were to look at the ratio of sides, look at the gradient, this side, the x is about twice the y. In this case, in our case, we are saying for every 8, we have 4 there. That is what this means. Right. Everybody see that? Kind of hard to understand. Eh? So that's what the 4-8 means.
Sir.
Yeah?
Yeah, this kind of make it much easier to understand.
Okay. Note, however, you realize the 4 here is on the y-axis and the 8 is on the, because really it's the slope of this line that it gave you. Slope of the tangent. So this is 8 and that is 4. Okay? So the steepest descent would flip it. Alright? Makes sense. So,
sir, you're saying it should be 90 degrees. You mentioned something about 90 degrees.
90 degrees. May I say something about 90 degrees, guys? Oh, yeah. The ascent. Hold on. Right. So this here, the ascent or descent. In this case, actually, I think this would be the ascent, right? So this is the minimum value, and we keep going up in this direction. So the direction of ascent is 90 degrees to the direction of the grad. Okay? The grad being 4, 8. Grad being 4, 8. You know, so we make a silly mistake here. You know what my mistake is? Let me show you what my mistake is. You see, when you're plotting on MATLAB or Octave, every column is actually an X. Column is an X. Let me put it this way. Let's look at. Let me make it That's right. Columns are X. Rows Y. Column Y. That's fine. So I think let's just do a check. Let's do a check to see what is actually being plotted here. I want to make sure the Z is on the right one. The Y is on the right plot on the X. Alright. Okay, so there's a value here for X equals 4 and Y equal this is about what? Oh, sorry, you can just take it from this side. X equal 4, Y equal, this is about 0.43, a 3 something. Let's say 0.35. What is that value? So Z is equal to 4, 0.35 squared. What's that? 0.49? Yeah. Okay, so this must be, so that can't be right. Alright, let's change it around. Let's say this is 0.35 and 4 squared. What's that? 5.6? That sounds better. Because, why? Because, is it 5.6? It's probably 5. Alright, what if it was this value, which is about double that? That's 0.7 and 4 squared, what's that? This is about 10. So this must be 5, 10, 15, 20, 25 and so on. Yeah, I'm pretty sure. Because 8 is here, right? But we know this is where 8 is. So it couldn't be the other way. So this is actually plotting the Y's on this axis and the X's on this axis. So I have to figure out how to make MATLAB do it the other way, but I'm not very excited to that. Yeah. Yeah, it's really that, just that, but actually making the right statement. Okay, let's do it. So you would say this is X and then you say this is Y and Z is, to be careful, Z is going to be that times X. Realize why I changed it, right? Because the row must come, the column must come first, then the row second, right? And then I do the contour of that now. Oh, plot quick this time. Oh, there we go. Can delete this one. The other one. One second, please. There we go. I just switched it. So everybody realized the plot changed, right? Huh? So I'm going to remove the little tricks of the trade. Come on. You realize I changed the order, right? I did. It is zone out, yeah. So yeah, here we go. So this is it. So now the slope is exactly as the grad. So the line of sequence descent is the grad. Note, we calculated the grad to be 4.8, and our line of ascent, if this is our gradient, like that, everybody agree about that? Then the line of steepest ascent is about that. And that slope is 8 on the y, 4 on the x. Alright? Simple as that. So what we do, so what the method does, is after you calculate the grad, then we say we're starting at a certain point. Let's say we start at this point. We say we are going to make an incremental step in from this point. So this is going to be x naught, y naught. And you want to know where is your new location that you're going to guess. You have to pick something called a step. Alright? So you're going to step in a certain direction. So what you do is you say, let x1 be x0 plus the grad function. So in our case it would have been 4 times your step h, and let y1 be x0 plus 8 times h. H is just a step. Alright? So if I wanted to step by 1, then what would x1, so this was let's say x naught was equal to 2, or xy. Let's write it this way. X naught, y naught equals 2, 2. Then x1, y1 equals, if h equal 1, I'm just picking an arbitrary value. If h equals 1, what is x1, y1? 6 and 9 you say? 10. Oh. 6 and 10. So, going back to the diagram. Oops, that's not correct. That was my last line. So it's going to go from 2, 2, and you'll jump all the way to 6, 10, which is not on this, but it'll be in a certain, somewhere up here. So if I wanted to make a smaller step size, so it can just be on this plot. Let's say I'm going to go by point, let's say 0.2. Then what would it be? X1 0.2, 0.1. Let's just say 0.1. And what would the new location be? So it would be 2 plus 4 times 0.1. 2.4, and the other one would have been 2.8. So 2.4 about here. Use my ruler. It's about 2.4, right? X equal 2.4. Y is about, this is 2, this is 3. 2.8 might be about there. 2.8 to be about here. Using my ruler. See, that's where it goes. So my first would have been there, and my step would have carried me to that location. So what you see is that I am moving up the slope. So when you use the steepest ascent or steepest descent, you move directly up the slope. It's like if you have a hill, you want to get to the top of the hill the quickest way, you take the steepest way to get up to the top of the hill. Alright? So that's the method of steepest ascent or steepest descent. So all of this is the same. Sometimes, as you can see, you have to do incremental search along the line of maximum gradient. So you have a fixed step. Sometimes your step might be too big. Remember just a while ago I said a step of 1? Sometimes when you take a step and you know you're going uphill, but when you take the step, you go down. That means you went past the peak. So you have to correct your step and make it smaller. Okay? So that's what step 3 said. So you look for when h is smaller. And also, how do you know you reach a peak? You reach a peak when your grad changes direction. Alright? Grad change in direction means the df dx changes direction and the df dy changes direction. Both of them will change direction when you reach a peak. All the time. You can use any one as a test. Both could have been positive. When you reach a peak, both will become negative. One could be positive and one could be negative. When you reach a peak, one will be negative and the other one will become positive. That's how you know you reach a peak. Alright? But as long as you're doing steepest ascent, they're going to stay together. Alright? What else? Now, this is now where it kind of rubber hit the road. Sometimes you don't actually have a function. What you have is just a complex system where you have an input and the input results in some effect and a multiplicity of effects. The point is though, at the end of it all, you're able to determine the value of something that you want. And that is what you're trying to optimize. In such a case, you don't necessarily have a clear function that you can differentiate or do things like that. And in all such cases, you have to use little steps to estimate your gradients. Alright? How do you estimate your gradient? You take a little x and a little y. Because remember, that's what partial derivative means. Assume one is constant, you take the x. Assume the other one is constant, take a y. Then from the little step, you get an estimate of the gradient. And then from that gradient, you do the big step. Understand what I just say? So let's say you have a system where you have a function that you can't differentiate. What you do is you calculate the function at a little increment around the location, holding one of the variable constant. Then calculate the function, holding the other variable constant for a little increment. Use both of those to estimate what is the gradient of that function. And then with that, you do your step using your regular incremental step size. Alright? So this is the general procedure for steepest ascent or steepest descent. Any questions? Rough stuff, eh? Stop rubbing your head, man. You know something. Alright, I'm gonna call me somebody WhatsApp me tomorrow if you don't see me. Put the next project, post it as it.
And then change sign means that we use the x value before then change sign, x and y value before then change sign as a solution.
Come again, say that again.
Iterative method as we find a solution, right?
Yeah.
So using this method, we use the x and the y value before the sign change as our solution.
Or at the sign change. Yeah.
Or at the sign change.
Yeah. What you'll be doing, you know,
So
you're going to take a step, right?
Mm-hmm.
And your step may actually work. That means every time you take the step, your function is getting larger. That means, remember you're doing the direction of largest gradient. When you take your step, you should also calculate the function. Or let me say it this way. Calculate the gradient, calculate the function. But the point is, when you confirm that the next value for the function is more than the previous one, and you say, yes, I'm going in the right direction. Eventually, if you use the same step, you will jump over your peak. So that's when you cut your step size. Normally, it's normal to say cut it by a half. So you start with a certain step size, and the step size will work, and you'll keep going up and up and up the slope, and suddenly you'll realize, I'm no longer going up, I'm going down. The moment you realize you went down, you step back, you cut your step size in a half, and then you step again. And then you're continuing stepping at that new half step until when you take that half step again, it went down, you step back and you take a quarter step, and you do it like that until you reach to your peak. Understand? And by the way, you reach your peak when just as with optimization, when the step size becomes, in optimization, it's when your range gets as an acceptable error. Your range is what gives you your error. So the same thing, your step size is what is going to establish your error. So when your step size goes down to 0.001, then you say you reach your peak. That means any more step and I keep going down, that means I reach my peak. Alright? So you use the increment, just like how you use the bound in bisection or golden section. How narrow has it gotten? Or in bisection, how narrow has your gap gotten? You know you reach your solution. Same thing. You see when your step size gets so small, you say, okay, I've reached a peak. Alright?
Sir, you have any animation?
Do I have any animation? I will have to look up an animation for you. Let me see though. Yes. Somebody said they want to see a animation.
How far?
I'll double check tomorrow. Yeah, man. Yeah. You might be fried. You might find yourself use it. You might find yourself use it.
That's what we said about
What?
Them couldn't teach me this high school. No, but they couldn't teach me this high school. You better me the one that we come from, then they go tell me science. So, just confuse me. Yeah, I know my high school brain never developed enough for this.
So why is not original help on him?
Minecraft? No, it's a electric man, and I know some other brands of slides. Right? So, I'm going to ask you design of experiments are only linear relationships. Okay. Like when we generate with your factors, they give you some coefficients, the regression equation. Yes, again with different variables, but then x1, x2, x3. So you wouldn't get like x squared or any x.
Sure, me see.
Yeah, that it's impossible to give. I stand.
Yes. Yeah, man. Some of them do.
So we give a like relationship at elements and stuff.
I remember some doing that.
Such
Some software like. Which one do you use?
we use many different spaces.
I know.
Yeah, I know, but it's one of them use.
Okay, but I think I know how to use quadratic. Yes. Let's see. tell him here. I want to tell him.
So finish your report, huh? Finish your revamped report.
You want? Oh, there. Send it to me, no? Please.
So just email it then. Alright. Email it then.
Upload, man. I still haven't seen many presentations.
You're supposed to do it
But don't do the presentation, just send me a presentation.
Upload it and set it on there.
You never, you
I want to
never.
group upload.
Same group.
Yeah.
Presentations. Hello? You guys had it in your presentation PowerPoint? You did? What about you, Paul? No, you're not. Jordan? You're gone?
Sir, but our abstract is different now.
Alright.
Alright.
But abstract was already on the name. That's fine. Your abstract for your report can be different. First one is the abstract for the presentation.
Because we weren't finishing the presentation.
So, everyone else who is there, nobody else. Richard, you have uploaded your presentation already? R12. Jayan,
she's Paul's leader. Paul. Jayan.
Jayan,
When we spend
Jayan,
Axel.
Jayan, hello.
Oh, you lose a voice. Come stay with me.
Yeah, come back to you.
Why?
You don't come back. Alright, look like everybody gone, so I'm going to start this recording. No, they still log on, but they drop asleep.
Double check, see everything tonight.
So who projects it during the presentation?
Okay, I almost said German groups and family. Practice question.
It should be there, right?
Yeah, and
You can go back through because some of the changes take place. I never really much.
Yeah, I never really much. Yeah, but I remember them I really get the options and when I options and changes.
Oh, okay.